Thank you. Good afternoon, everyone. So my name is Shweta Raur. So I'm from VMware by Broadcom, and I work on the product called Greenplum. So I have around 18 years of experience in the IT industry, and most of my experience is in the operating systems. And 2 years ago, so I shifted to DBMS and Greenplum. My journey with Greenplum began from there. So let's look at the agenda for today. So we're going to give a very brief introduction about our product, what is Greenplum, and touch upon very briefly on the architecture of Greenplum, and also give you some idea about what are the capabilities of Greenplum. And then we will move on to the actual topic of today, that is the geographic information systems and the PostGIS and Uber H3. So that is going to be the agenda for today. So let's get started on what is Greenplum. So Greenplum was started in 2003. So when it was the era of internet and the data started growing, it became like petabytes and terabytes of data. So our founders started Greenplum with the intention of bringing efficiency in handling of huge amounts of data. So it took a few years, around 2007, so when the product became sellable. And in 2010, it was purchased by EMC. So that is also when Greenplum became enterprise ready with the mirroring and high availability solutions. So even today, Greenplum is mainly used by enterprise software and enterprise solutions. So in 2003, so Greenplum aligned with Pivotal, and that 2013, it aligned with Pivotal. And that was also the year where it was spun off from EMC. So, and then in 2015, so it became open source Greenplum, and even today it is open source. So the code is, all the code is available on GitHub. So if anybody is interested, feel free to go and check what Greenplum is. And that was also the year where GP Orca, the optimizer, was introduced. So Greenplum is nothing but enhanced PostgreSQL, so Postgres on a distributed environment, and most of our IP is in GP Orca. So this is the one that is responsible for giving analytical capabilities to Greenplum in data warehousing solution. So this is also open source as well, so if anybody is interested, you can feel free to go and check the code and see how GP Orca works. So in 2017, Greenplum also became cloud ready. So it is supported now on AWS, Google Cloud Platform, and Microsoft Azure, and we also support on VMware vSphere. So 2019, VMware acquired Pivotal, and that is when we started making more releases, more investments came in. And the latest release is Greenplum 7.x, which supports Postgres 12.4. So now recently, Broadcom acquired VMware, and Greenplum is part of Broadcom right now. So that's 2 decades of Greenplum history. So what Greenplum does as a product. Why is Greenplum necessary? So let's touch upon a little bit of these concepts as well. So as and when the data increases, right, so it becomes terabytes and petabytes of data. So if you consider a scale-up architecture, so you have to go and keep on buying bigger and bigger machine. So this might not be a viable solution always. So instead of scale up, why don't we look at a scale out architecture where if the data increases, so you can increase your computing power and you can increase the number of Postgres instances that are there. So to just give an analogy to this instance, right, consider a person who has the habit of collecting business cards. So he has around 100 business cards, and which is arranged beautifully in alphabetical order. So and it's pretty easy for him to go and look up the card he wants. But if the card becomes 10,000, so if he has 10,000 cards, the same activity could take him 10 minutes or even more. So what the scale out architecture does is, hypothetically, let's say that he distributes these cards among 10 different people. So each of them have 100 cards each, and when he wants to look up a card, all of them parallelly search for that card, and any card you can search in a minute or less than a minute because of that parallel processing. So that's the basic idea of Greenplum. So that's what Greenplum does. So it's enhanced Postgres SQL. So it has multiple Postgres instances which are cohesively working as one single unit. So that is to summarize what I already said. So it's enhanced Postgres SQL and it's massively parallel processing. So and though it's massively parallel processing, so it has a master node which takes care of the metadata and it takes care of query processing. It has a segment nodes which actually contain the data, and all these segment nodes do not share data amongst them. So it's a shared nothing architecture. And it's specifically for big data analytics and data warehousing, so it can support terabytes to petabytes of data, structured or unstructured, BI or AI analytics. So Greenplum can handle all of it. So, okay, so let me touch upon the Greenplum architecture very briefly. So as I said before, so Greenplum has a master and segment nodes. So master, we have renamed it to coordinator in 7.x. So the master is the entry point to the system. So this is where the query, the user connects to the cluster and he executes the query. It handles all the user connections and it creates query plan. The Orca that I was talking about is part of Greenplum. So it processes the queries, creates a plan, and that plan is dispatched to the segment nodes. And once the plan is executed, the result is aggregated and then returned back to the user. So Orca, again, it's open source, so that is where our IPs are. So as opposed to the Postgres planner, so it has limitations, the legacy Postgres planner, because it works on single nodes. But if anybody is using distributed systems and they want a highly improvised and innovative optimizer, please feel free to look at Orca. And it also has metadata, it contains of metadata, and it manages, it knows all the information about the hosts and the segment nodes that it manages. So in between master and segment host, we have an interconnect that is like high-speed software, so which is streaming data tuples to the segment nodes. And apart from that, we have the segment nodes. So each of the segment nodes is scalable, so you can have a container, you can have a VM, or you can have a bare metal, and you can scale the segment nodes. But there is no direct entry point to the segment nodes. You have to connect through the coordinator, and that is where the actual data resides. The coordinator does not have any data. So the entire code of Greenplum is available. It's open source. It's available on GitHub as well. So to look at some of the capabilities of Greenplum, right? So it gives a network, storage, and compute, and if you can create a massively scalable compute grid, which is high performance for high performance computing. And you can connect to this high performance computing using the traditional methods or programmatically via programming languages such as Python and R, so which is the data scientists are most comfortable with. So in addition to that, it supports traditional row-oriented queries as well as columnar storage. So this columnar storage is the distinguishing factor of Greenplum. So it is used in analytics where you can see increased in performance. So along with all this, so it understands that not all data is structured. So there is support for structured, semi-structured as well as unstructured data. And of course, it's based on Postgres SQL, which is one of the most amazing database, open source databases of all time. So along with this, so we understand that not all data resides in Greenplum. So there could be data outside Greenplum as well. So there is support for federated query processing. So there is a federated query processing engine which is native to Greenplum, so which can be used to process these queries. So along with this, it supports features such as time series, graph, and geospatial. So geospatial is one we're going to touch upon as we go on in this presentation. So along with all this, it gives capabilities for enterprise search patterns. So these are some of the capabilities that Greenplum offers. So along with this, so it is supported on multiple infrastructures, multiple operating systems, Red Hat, SUSE, Oracle Linux, or Ubuntu, and it is also supported on containers, and it is supported on cloud, Amazon Web Services, Microsoft Azure, Google Cloud Platform, and VMware vSphere, and also on bare metal. So these are some of the infrastructure agnostic capabilities of Greenplum. Okay, so let's move on to the geographic information systems. So before we start the presentation, so let's look at some of the terminologies and understand like what is map and computer map. So when we were children, right, I remember we had colorful books called atlases. So all of us had atlases in which we used to go and look up the countries, the continents, and the entire earth. But now we all know that the entire map and data is digitized, and even if we have to go from one location to another location in the city, we end up using our Google Maps. So, but have you wondered like how these Google Map work and what are the kind of data structures or the information systems that they use? So let's understand that, and let's move on to what is a geographic information system. So what is it? Before that, what is geographic data? So geographic data is something that has geography associated with it. Latitude and longitude is associated with that, that becomes a geographic data. So, and if you associate any attribute with it, such as the population, the flooded zone, land covers, elevation, any data, extra data attributes you're associating with that data, that becomes geospatial data. So, and if you want to analyze this data and come to some conclusion, you need a geographic information system. So what geographic information does is it divides the real world into multiple layers, so analyzes, identifies patterns, trends, and gives you a visualization method which is not easily available with other methods such as columnar data or text data. So yeah, so as we saw in the last slide, GIS analyzes the data and gives you a visual map. So it also stores and manages and displays it on the top. So, but how does this store? How does GIS store this data? It stores this data in the form of vectors and rasters. So vectors is represented by points, lines, and polygons. So these can be used to represent city roads, boundaries, etc. using vectors. But raster data is represented by squares or rectangles or pixel. You can call it pixel and you have a value associated with it. That is raster data. So I mean Rakesh is going to talk in depth about like vectors and raster data. So that's the, I hope like we can give a basic idea. So why do we need this spatial database? So we are seeing nowadays this geospatial database is being used everywhere. The volume of the data is growing day by day, and you need a good spatial database to analyze all this data. Similarly, the complexity is increasing. As more and more people adapt geospatial database, more and more relationships are developed, and we need to analyze this. And also, the interdisciplinary applications of this is growing day by day. So considering all these factors, so you need a good geospatial or the spatial database system. So, and having this background and understanding all these terminologies, let's move on towards PostGIS or the spatial database. So with this, I'm going to hand it over to Rakesh, my colleague.
So till now we have discussed about the Greenplum, its capabilities, Orca optimizer, and the extension it supports. And we discussed about the GIS data and how the standard database is not like up to mark to store those data. So we'll talk about what is the like differences between the standard database and our spatial database. So in a standard database we have primitive types like strings, float, date, and we have indexes which works on those primitive types like B-tree and hash, and the function which operate on those and give some result out of those data types. So every database have three essential parts. One is types, indexes, and functions. So if we geospatial data is a specific data which is either let long, which is in degrees, and or the geometry specific data, and we have the raster data and some other data as well. So major data type, the problem with the standard database that it cannot be able to handle the degree data and that points and geometric related data, and because of that it was essential to have a spatial or specific data type, special data type which can handle geographical information, and it can work on that and can analyze on those things. So in a special data database, we have types like geometry, geography. We have raster, which is supported with a separate extension called PostGIS raster. Then we have spatial indexes like R trees, quad trees, KD trees. We have other indexes from Uber as well as S3, which we will talk about later. Then we have a spatial function, like we have a geometry, we have a 2 points. This like always reasonable to have that length function, area functions, and get some points from that. So these are the different difference between our standard database and the geospatial database. So for that, if you are developing an application and which is like on the PostGIS, and you want your GIS capabilities on those applications, if you are dealing with the maps and all, so you can install this extension PostGIS on top of the PostGIS. So it extends capabilities to store geospatial data, does the indexing on those data and querying geospatial data based on the our requirement, for analysis and those things. It was developed in 2001 at Reflection Research by Paul Ramsey, and it was this is extension which we can use in the similar fashion, similar SQL queries with the similar SQL queries which we used in the PostGIS. So it is on the same line of the PostGIS. Now the key feature of the PostGIS is apart from 3 basic features which has a data storage, indexing and special functions, we have some functions or extended capabilities to basically manipulate the geometries, create the geometry. If you have a polygon, you can split out in 2 polygons. Then we have a raster data support, which is done by PostGIS raster extension. Then we have conversion from point to geocoding, basically long lat, and getting it back to the point from lat long. And this PostGIS is basically based on the OGC and ISO standards. So it does have the integration with the third parties application like QGIS, map server. So it does your application streamline from development to database to visualization. So in the major basic feature of the PostGIS is to understand the basic feature. Before that, we go with the map projection. So map projection is basically projecting a 3D surface point onto the 2D plane coordinates. So if we have a lat long point on the 3D surface, you can project with those projection to the 2D plane and create a geometry out of that. There are a lot of n numbers of projections available and theoretically, and they are majorly depend on 3 types. One is the equidistant projection, cylindrical projection, and conic projections. All the projections have their limitation because you cannot create a perfect geometry or perfect projection from the 3D to 2D. So it does have the distortion. PostGIS supports 2 major data types, geometry and geography. Geometry is basically, it is represented by primitive types like points, polygon, lines, and the geography data is represented by the degrees, like latitude and longitude. We have the more function related to geometry in PostGIS rather than geography because the calculations always, for the geography, it takes a lot of CPU cycles because it does in a 3D space. Like for example, if we have 2 points, point A and point B, and we want to find out the distance between both the points. In the planar geometry or 2D plane, we can have the simple calculation to get the distance between 2 points. But in 3D surface, the point or distance will be a max arc length, and there comes the calculation around the radius of the geometry and sine cosine. So that's why it takes time, takes more CPU cycles in the geographic calculations. Under the geometry with spatial reference ID, we have these many primitives type like point, curve, surface, polygon, line strings, and we have geometry collection types as well. So spatial reference ID identifier is basically It provides you like give you an attribute of a coordinate system, like which coordinate system the particular geometry or geography type is using. When you install the PostGIS in your database, you will find a system reference table in there where you will get all the SRIDs. I think there are 8,400 around SRIDs available. Now we walk through some of the examples. Like for this, these queries, I have taken the OSM dataset and the NYC dataset. So in the first query left side, like we are finding the distance which is in degrees. Basically it gives the direction. So if your ST distance gives the direction between the 2 points, and we have associated SRID with point Los Angeles and the SRID with point Paris. So both are on the same coordinate systems, and we are running the query to find out the distance. So it gives the distance 121.89, which is in degrees. So basically it gives the direction from Paris to Los Angeles. And when I run this query on the Greenplum, which is MPP architecture on the PostGIS, it took around 8 milliseconds, and on PostGIS it took around 17.9 milliseconds. On the right hand side, like we are finding the actual distance in meters between those 2 points. So you can see that all the queries are same, both the queries are same. The only difference is in data types. So in left side we are using geometry, and right side we are using geography. And this gives that distance output in a meter. So you can say that 9,124 kilometer when is actual distance between the Paris and LA. When I run this query on the Greenplum, it was taking around 75.738 millisecond, and on PostGIS it was taking around 118 millisecond. The Greenplum is like 3 node cluster on the same host. So we have three nodes which was on the same host machine. And you can see like the calculation between the geometry and geography. Geometry was taking 2 less time, like it was taking around 8 milliseconds. But the calculation on the geography part, it was taking more time. So that's why we have lesser function related to geography. And it provides like PostGIS also provides like typecasting between the geometry and geography. So you can see the same function takes geometry as an input, and same function takes geography as an input. This query, it does like how you can do the typecasting between geometry and geography. This table I have created because I am using this table in further examples. Now you want to find out Empire State Building, like nearest metro station to the Empire State Building, and which in the perimeter of 500 meter. So we have the one point which is representing the Empire State Building, and we are finding the distance as well as degrees, like directions as well. So these two functions we are running, ST distance and degree. And this ST, this one azimuth is like basically a projection, map projection in equidistance. When I run this query on the Greenplum, it was taking around 139 milliseconds, and on PostGIS it was taking around 744 milliseconds. So, and it does gives a meter distance in meter and the degree, basically a direction. Okay. So here you can see the query are taking a lot of times. So how can I increase those times? So for that, the second part of the database, any database comes in a picture, where is the indexing, which narrow down the search space and find out the best optimal result for you. So in PostGIS, we are using R3 based indexes. Basically what it does, it divides all the attributes or entities into the polygons or hierarchical tree of rectangles. So you can see in the right side of diagram where we have like a represented hierarchical structure of the rectangles. So for this example, if you want to find out the stars, which is under the D rectangle, how the query will go. So it first will search for the T and U, then it will go down, it will search for the NPQ rectangle, then it will go down and find out the result in the D. So that way we have to only touch the 8 boxes rather than touching the 13 boxes. So the indexing is like essential part for any database to like find out done the querying in the fast possible way. Now I have created an index on NYC subway station data, like between the NYC on NYC subway station. So here we are running the same query to find out the nearest metro station to the Empire State Building. So it's the same query which earlier was taking around 139 millisecond on Greenplum, and on PostGIS it was taking around 744 millisecond. Now after indexing, it took around 22 millisecond on the Greenplum architecture, and on PostGIS it was taking around 122 milliseconds. So by this indexing, you can you can make a faster query or get the faster result. So till this point, we have discussed about the geometry, geography, and we have run some example on that. Now there's one more data type which I talked earlier, was raster data type. So raster is basically n-grid architecture, n-grid 2D dimensional grid, where you have the pixels definition. Basically, when you take picture from your camera or phone, it will give you a 2D or basically raster data on that. And raster data on each pixel have some values which it depends on its band. So like in this example, we are taking a 3-band structure where values are RGB, red, green, blue. Based on that, the pixel values are assigned. And raster data is basically we used by overlapping on vector data. So vector data on the map, it gives us the direction, roads, and the boundaries. But raster data gives the actual land positions, like what is the condition of the land. We can use these raster data in disaster, risk management, risk assessment, disaster management, then land use changes. We use this data onto the we use satellite images basically, which is a raster data again. We use that in our border security situations, like how the troops are moving from one side to another side. So these are some of the examples, and the weather data, like the temperature which comes up on the news, which is basically shows the raster data on your earth, or basically on the map. Now till now we have discussed about all the things related to PostGIS. We have discussed about the arteries, which is basically indexing, and it was fast, it was essential to find out the best possible result in faster way. But Uber was facing some other problems, because they need to find out the location of the nearest in some kilometer or some meter. So when you book a cab through Uber, it will basically connect you with the nearest cab provider or cab service or cab available from your point. And the problem with the artery is there was a lot of overlapping rectangles, and you cannot find out the distance or direction from one rectangle to another rectangle. So S3 work on the indexing part. So S3 is basically indexing on your PostGIS data. So Uber work on indexing part, and what S3 does, it divides your or partition your earth onto the hexagonal grids of different sizes. So S3 is again open source geospatial indexing. It was developed by Uber, and it gives you a hierarchical grid structure, from 0th resolution to 15th resolution it has, and it gives you aggregated, and it is most useful in finding the nearest position, or basically you want to run the KN and K nearest neighbor algorithms or those cases. It basically uses a Dimension map. It's a different kind of mapping or projections from 3D to 2D. Why they use Dimension map? Because all the distorted point for this projection or 3D was falling in the ocean. So that was what this was most suitable when they were designing S3. And S3 comes up with all the kind of binding with all the programming language. So you can use this S3 in Python, Golang, and other programming language as well. So this S3 does. So first it partitions the world, then it does the indexing, and then it runs the algorithm to find the nearest neighbor. So like you are in the second picture, you are saying the points. So when when we compare with the same index, if it is falling in the same index and we compare with the index ID for each points, and that way we can fastly tell that yeah, it's on the same or nearest location. Each hexagon with different resolution, it has their own basically length in a kilometers or own size. This was run on the OSM database, basically OpenStreetMap database. So I have created one index there. Okay, and this index basically represented by a hexagon on the map. You can see the green, blue dot on the map, and you can see S3IX, which is a basically hex index. It is a 64-bit data structure. Then when you expand the boundary along with that index, you can see this kind of a structure, where this is covering the like some part of the earth. Okay, so why they choose hexagon? Because there are other primitives type also available, like triangle and square. So you can see in the triangle we have 12 neighbors, and each neighbor and 3 different distances among the neighbors. Like you can see here, what is it? You can see here 3 different distance. Like one is this, second this one, and third one. So we have 3 different distance to the like center triangle to the each neighbor. And also what this is like a basically ambiguous neighbor, because only vertices connected between the 2 triangles, not the edges. Here we have 2 different distances and 8 among the 8 neighbors. But in a hexagon, we have the unique distances among the all the 6 neighbors, and there is no ambiguity between the neighbors as well. So it is perfectly connected with the edges. You can see, and this way, like if you cover this entire portion of 7 hexagons, it will be a like approximation to the circle, which gives you a better result when you find out the nearest neighbor. That's why they choose the hexagon. In this, I have created a one index, S3 index, and I have run the query to find out the trees among the within the 10 kilometer focus point or 10 kilometer area. When I run this query on the PostGIS with the artery indexes, it took around 14 to 25 milliseconds in a different run. And on the right hand side, when I run this, it was taking around 4 to 6 milliseconds. So that way, finding the nearest neighbor or the approximation area within the parameter is faster in the S3 with the S3 indexes. And it was returning around 12,000 rows. So this way, S3 is very useful when you are running the nearest neighbor, or you find out the nearest point on from the locations. We talked about the resolution. So S3 supports resolution of hexagons. Resolution is basically the size of the hexagon. So when we talk about the 0th resolution, the size of the maximum number of the hexagon on which are covering the earth is around 122 hexagons. And when we narrow down to 15,000, it comes with an 15 resolution. It comes number around these things. And the distance of the size of the distance between the 2 hexagon, when we create an index in 15 resolution, it's around less than 1 meter. So these are the different number of cells for the each resolution. I took the difference of 3 because of the slides. So 0, we have 122 hexagons on the earth. On 15, we have 5, 6, 9, and some numbers of that. So this way you can with the help of PostGIS on top of the PostGIS and with S3 indexing, you can basically take advantage in your applications. So this was about the S3. Then future extension to Greenplum. So these already supported in the PostGIS, like 3D-CTDB and PGConf Cloud, and we are planning or in discussion to have these 2 as well which is again related to geospatial in Greenplum. So 3D CityDB is basically GML language, is based on the city GML standard. It was again based on the OGC, and the PG point cloud gives like basically it gives a number of points or which is like again attached together. It is helpful in 3D scanning and 3D printers. So both we are targeting for the further integration in a Greenplum. These are the resources I use to create my slides. So you can go through those resources. All are like well articulated. Yeah, thank you. I think we are open for question. So for the performance number, it was basically on with the Greenplum against the PostGIS, not related with the S3. And in the Greenplum on the same host, if you like divide the same task to 3 different nodes in the distributed architecture.
Hardware for Postgres and for Greenplum.
Sorry?
So you used multiple nodes for Greenplum? And
yeah, multiple nodes we used the Postgres for the Greenplum. So there was 3 nodes of the Postgres was running when in the Greenplum. So you can say there's 3 instances of Postgres which is connected to coordinator, and we distributed all the queries among those things. So that's why these results is the difference between the Greenplum and Postgres.
So the difference that you see is because of the architecture of Greenplum. So Greenplum is Postgres only, enhanced Postgres, but it's multiple instances of Postgres is running massively parallelly. So that's causing the difference.
Each instance runs the same, PostGIS was the same, the library is the same.
Library is the same, but the underlying
data distribution and those things come here. The Orca optimizer, those comes in a picture for the Greenplum.
We have an optimizer in Greenplum, so which distributes this processing across like say 10 different Postgres instances. Because I am working parallelly, you are seeing the difference.
Thank you. No.
Should be different providers or different way of working versus the green, right? Because that confused me also. When you're comparing the query of
yeah, I agree. Yeah. So that's why we initially discussed about the Greenplum, how Greenplum works. And I also mentioned that I'm running these queries on the Greenplum with 3 nodes. 3 nodes means 3 Postgres instances. So maybe I was not clear with the slides or the numbers.
Second question is around like the S3 versus Postgres.
Postgres, yes.
So S3 is a separate, S3 is a separate extension, or what is it?
S3 is like library which you can bind with a PostGIS as well, and even other languages as well.
So again, that is also considered here. When you're comparing the PostGIS versus S3.
So I told the PostGIS has the R3 indexing by default, and S3 is a different set of indexing. So it does the indexing on the PostGIS.
But okay, this means that it extends the indexing.
Yeah, so that was basically a difference between the R3 and S3.
I have one question here. At one point, you displayed the demonstration for calculation between distance between 2 points, Paris and Los Angeles in that case. So there, in my opinion, it was just a static calculation. It was not reading from any node. Okay, when it comes about NPP that Greenplum has is virtual, but the calculation, the timing PTA for Greenplum and Postgres was different. So how you are portraying that? It's a very static calculation. It did not have anything to read from 3 nodes or a single node. So why that calculation was different for Postgres and Greenplum? Are you trying to say that any difference between the usage of hardware between 2 engines, or is it a virtue of Greenplum to make it more faster than Postgres? Because it was just a static.
Yeah, so both are numbers, points in it. Like even No, even it is static. It does calculation of the like taking a like it takes the input from the SRIDs, tables, and all, right? So it does the processing and aggregation, and Orca comes in a play. But again, like I mentioned, those things with the SRID. So SRID information is available in the tables. So it is not completely static one.
Amount of data is there, more amount of data, then that Greenplum will take regularly than the PostGIS.
Even SRID table has 8,400 rows.
But that is completely a computational aspect.
Yeah, computational aspect. Yeah, yeah. The main intention is like when you computing power, right? You can increase the computing power with the help of Greenplum.
Thank you so much.